Continuing where we left off. Whether you're north of the equator or south of the equator, your compass needle still points north because your compass needle has a south end and that is attracted to a north pole, right? Opposites attract when it comes to magnets. Now, something else goes on with the Earth's magnetic pole called a reversal. And in that case, your compass needle would point south, no matter where it was on the globe. And this has happened in the past. The last time it happened was about 700,000 years ago. So for example, 800,000 years ago, everyone's compass needle would have pointed south. These are also recorded in the rocks. So Earth's magnetic field occasionally changes what we call polarity. So a normal polarity is similar to how the magnetic field is today. Your compass needle would point north. A reverse polarity means that it would be pointing south. So here's a chronology of the past 4 million years. So this is just a very, very recent bit of time with the present at the top and 1, 2, 3, 4 million here. And these are magnetic reversals. And they have names: Bruns normalchron, Matayama reverse chron. You don't have to worry about the names. People take paleomagnetic samples and we can tell if they're normal or reversed. By looking worldwide, we've been able to see that there was a period of normal polarity that exists today, but it began about 700,000 years ago. And between about 2.5 million years ago and 700,000 years ago, there was a major period of reversed polarity. Now there's these little things called subchrons and there's excursions, and it's all much more detailed than I'm making it. But for simplicity, we're going to just say that this is a period of normal polarity, reversed, normal, reversed. How does this happen? Good question. There are many different controversies about how this happens, and it hasn't been quite figured out yet. So we're not really sure how it happens, but we do know that it happens. Now, what does this imply about rocks that are magnetized? So here's a volcano, and here's the normal magnetic field of today. So imagine in this particular area, this is how the field lines are pointing. And we know they're in the northern hemisphere because they're pointing down. And they're at an angle because they're somewhere between the equator and the North Pole. This could very well be Pasadena. So rocks erupted most recently here from this volcano 0.4 million years ago. Well, that is 400,000 years ago. And that's when we still had normal polarity. And so the little magnetic minerals in those rocks are still recording down into the north. 0.8 million years ago, or 800,000 years ago, we were in that reversed polarity chron. The little magnetic minerals in those rocks are going to record up and to the south. Going back in time to 1.2 million years ago, when we were back in a period of normal polarity, the minerals record down and to the north. So we have a chronology of the reversals, but what would really be convenient would be to have a place where we have continuous volcanic activity. Not like a volcano that erupts every couple 100,000 years. Where is it on Earth that we have continuous volcanic activity? Do you know? At the seafloor spreading zones, at the divergent plate boundaries. Remember, new material wells up, forms new seafloor, and moves out to the side. We constantly have new seafloor forming at spreading ridges. And so like a conveyor belt, the old crust moves to the side and new crust forms in the middle. So here's a cartoon showing 3 different time periods. This one shows positive signs where new seafloor is spreading and recording normal polarity, like today. And what's been pushed to the side is older crust that had been recording reverse polarity. Now in time 2, those pieces of ocean crust that recorded normal polarity have been pushed away, and new magma is coming up and it's recording reverse polarity because at this time period there's reverse polarity. We go on to time 3, and now that's been pushed to the side, and now we have a normal period, and now the new ocean crust is recording that. It's almost like a scanner code when you go shopping. It's got a very unique pattern, and importantly, it's symmetrical about the ridge. This side mirrors this side because they're both spreading symmetrically away from each other. Now, how do we measure that? Well, ships, such as this one, travel over the ocean crust, and they record the strength of the magnetic field in the ocean crust. Now, this has been false colored. Obviously, the ocean crust isn't colored. But what they've done here is they've put white colors for normal polarity and then this kind of pink color for reverse. And so as the ship goes over areas of normal polarity, such as this white area, they get a high intensity signal, a strong signal, because you've got the normal polarity of today combining with the normal polarity of the rocks, and so they together give you a strong signal. When it goes over this area of reversed polarity crust, then today's signal and the rocks kind of cancel each other out, and you get a very weak strength of the signal. Most importantly, back to this diagram, and this is page 22 in your lab manual. You're going to be working with this week in lab. These isochrons that I showed you earlier have been determined by these reversals. So this time scale down here, which doesn't look very regular, right? Well, there's a big giant green area here and a small orange here. That's because that time scale is actually linked directly to reversals. This period right here is actually called the Cretaceous long normal. It's a time period that lasted 40 million years where the ocean crust recorded normal polarity. There were no reversals. Again, we don't know why reversals occur, and they seem to occur randomly. There doesn't seem to be a pattern. But that's what you're seeing here. You're seeing the age of the ocean crust based on the magnetic polarity within the seafloor. And so this is really, really strong evidence of seafloor spreading. If Wegener had any idea that this was going on, he would definitely have understood that the plate in plate tectonics includes the seafloor. Now, just to show you that it's not really that ideal, this is off the coast of the US, and these are some marine, we call them marine magnetic anomalies, is another word for isochron. And this is showing normal in dark color and reverse in white. And this is the Juan de Fuca spreading center. So in theory, you should have a mirror image on either side here. But this is the reality of what these anomalies look like. It's really not that simple as this diagram right here. But still, people have figured them out, and they've used it to reconstruct the story of the plates. Our next unit will be looking at more evidence for plate tectonics, including hotspots and earthquakes.